So, good afternoon, start lecture. Okay, we'll continue on an example here. Just a quick review of what we did from previous lecture. Basically, we learned about the fatigue failure for ductile material. Okay, and we'll look at an example first, and then we'll finish with the ductile material, static failure for brittle materials. Okay, yeah. So here's a fairly quick review here based on this diagram showing it here, right? Yeah. Basically, there are two curves. One is an ellipse, the other is a hexagon. So this is basically the two theories that we learned from the previous lecture. The blue one representing the distortion energy theory. The dashed brown one representing this maximum shear stress theory. Okay, yeah. So you always have essentially three different types of loading conditions, right, or loading planes. Basically, it's a planar case, and then was put it into 3D perspective. Okay. So that's why you see the three different type of loading planes that are here, right? And for MSS, as we learned, your safety factor is always just SYT over sigma 1 minus sigma 3. And for DE, your safety factor is SYT over sigma prime. And sigma prime, if you recall that, is called von Mises stress. And von Mises stress, you can calculate it using the two principal normal stress. Okay. Or you can calculate it using the state of stress from the stress element. Okay. So either way, you can get the sigma prime. It will be the same. Okay. And MSS apparently, as we said, is a little more conservative compared to the DE theory because it's inscribed between the DE ellipse. Okay. So we start an example. We have basically a rod that here carries an arm. Okay. So the arm here, this is L, and this is your A here. And then there's a force applied at the end of the arm. The rod has a diameter D. So L equal to 6 inch, A equal to 8 inch, D equal to 1.5 inch, F is 1,000 pounds. Consider ductile material which has 47,000 psi. Okay. And we want to analyze basically this simple system and make sure it's safe, right? Yeah. And in previous lecture, first question we ask is, so which location we want to analyze? And then we basically wanted to look at the location that is the most critical location. And most critical location at the wall here, because this force F, right, will generate one is a torque, the other is a moment. So based on basically the distance of L and the distance of A, and you will have either a torque or moment at this base location. At the same time, because the F, so everywhere along the system, you also have this force felt by this force F. So the critical location we said is at this base location. Okay, and the base location, there are many locations around the circle. So we'll only look at two locations. One is the top, and the other is here. So this is A. Let's say this is B here. Because we learned when we do the review of the stress, at the A location you have a maximum bending normal stress. At a B location, you have a maximum shear stress. Okay, yeah. So those two maximum, right? Not necessarily means they are both the same, but we actually want to compare. We'll see that which is more critical, right? Is A more critical? Is B more critical? Okay, so that gives us more of a conclusion for us to make use of for the future. So for future, we don't necessarily have to always look at both locations, and we'll just have to look at one of these locations, which is one of the most critical out of these two. Okay, yeah. All right. So first step. Okay, for this kind of system, the first step is always free body diagram. Okay, free body diagram. Free body diagram meaning basically based on a given loading condition, right? You take the body out and then you draw all the external forces, and then you draw them properly. Okay, yeah. So for example, for this particular system, let's look at the rod at here. Okay, let's look at the rod. Yeah, and this is the arm at here, right? Yeah. So I'm taking out the whole system, okay, away from the wall. Okay? And you have your x-axis at here, okay? And then your y-axis at here, and then z-axis at here. Okay. And you have the force F over here, right? You got a force F here. Okay. Okay. So this is basically the only external force applied, but in order to balance, make it an equilibrium condition. So the wall, right? Basically, the location, the wall here will balance the whole system with whatever force or moment or torque, so the whole system stays in equilibrium. Okay, yeah. So basically, this side is a wall here. Okay, so you can think of the cross section on the on the inside the paper here. This is the wall location. In order to balance this force, what do we need? We need basically a force going up, right, to balance this F right here from the wall. So the wall has a force action reaction. At the same time, so if you think about it, and basically, so F times this distance, right? So this R cross F will give us a bending moment, isn't it, right? Will give us bending moment. Okay. So if you let's say call this is R1 here, for example. Let's say call this is R2 here. So the shorter distance from here to here, this is L and this is A. So if you use F times L, you got a moment, right? So this moment is gonna bend the rod like this. Okay, it will bend it like this, isn't it, right? Yeah. So R cross F is the moment, and it's bending like this. So from the wall direction, you should have a direction of moment to balance that out, which will be this direction. Okay, yeah. That makes sense? Actually, sorry. No, sorry, the wrong direction here. So it's this bending, right? So you bend F times A, will bend it like that. So that side wall will balance this like this. Okay? Can you visualize it? Okay. See, R cross F is the bending, right? And then you have this side here to balance it out. Okay? Yeah. So if you have a bar here, so it's going to bend like this, F times L is bend like this. On the wall, you should try to balance it like this, same direction, not same direction, different direction, right? Yeah. Okay. And then F times A, right? F times A here is R cross F, R2 cross F, will try to cause this rod to rotate like this, right? Yeah. So you have a torque which is trying to do this direction here. So then on the wall, that torque should be what? What direction now? From the wall side. It's this direction here, right? Yeah. So to balance this torque, okay. Yeah. So R cross F, trying to rotate it basically this way here. So then you have a counter torque to balance it out. Okay. So you have a T at here from the wall here. Okay. So I can calculate the numbers. You can calculate the numbers M. For the M here is what? The absolute value is F times L. Okay. And that equal to F is 1,000 and L is 6. Okay. So that equal to 6,000 pound-inch. Okay. So basically 6,000 pound-force-inch. And then the torque equal to F times A, which is 1,000 times 8. So that's 8,000 pound-force-inch. So that's the value of M, and that's the value of T at here. Okay. And this is your free body diagram, right? Now, step number 2, okay, is now we're gonna look at the location A and B, okay, and analyze the loading conditions at location A and B. Remember, A and B is the location here and here, right? This is location A and B. So for A and B, so what this step needs to do is you need to sketch a stress element at A and B. So you need to pick a stress element at A and also stress element at B. So then you sketch this stress element, basically the distribution of the state of stress for that stress element, okay, for A and B here. So how do we basically pick a stress element then, right? So to pick a stress element at A and B, so what you need to do is you can think about this. Visualize. You're going to do a cut, okay, vertical cut across this rod. Basically cut it across the rod just in front of the wall. Okay, so you cut it across the rod just in front of the wall here. So it's like, let's say for example, if this side here, okay, if this side is the cross section attached to the wall, then we do another cut right in front of it. Okay, so this is the side right in front of the wall here. So this is basically how you cut it. Is that good? So this is how you think about it. So cut a cross section in front of the wall. Okay, so just in front of the wall there. So this side is the wall and this side is the cross section. Okay. Yeah. And now it's very, very thin cuts, very thin, because you're taking a stress element here. So now we're taking stress element here, so we're going to take a stress element at here and also take a stress element at here. Okay. So before we take the stress element, so let's look at the cut it out piece of elements here. So this is what, let's say, maybe a slice of something that you cut it out from the rod here, right? So if you think about it, again on the wall side, what do we have? On the wall you have this is x-axis here. On the wall side you have a bending moment, just like what we just draw here, what we draw there. So you have a torque T and you have a F pointing up like that. Okay? Yeah. So what about on the cross-section side, the cut it out cross-section side, right? So we want to do the same thing. the bottom principle is what? This little piece, this slice needs to be in equilibrium. Okay, in equilibrium. So on this side here, in order to keep it in equilibrium, then on this side here you have what? You have a force going down, right, to balance that. And then you also have a torque to balance this torque, which is this direction. Okay. And you also have a moment on this side here to balance this moment. So that'll be this way here. Okay. So this is the precise free body diagram for that slice, okay, at the end of the wall there, okay, at the end of the rod. Okay. Yes.
Is the moment both going down like that, or?
Yeah. So this is balancing. This side trying to bend this, right? It's balancing here. You get it, right? Yeah. Oh, yeah. Otherwise, you'll start to rotate now, right? So once you have this now, then we'll think about the stress element now. Okay, stress element. So let me maybe redraw this here again. Okay, so just for the stress element. So here is one, and here's another location. I'm going to draw the stress element. Okay. So at A location, you draw a little bit a little rectangle. Then you can extend the rectangle to make it a cube, right? So extend it along the direction of the rod to make it a cube here. So that's the two stress elements here. Okay, two stress elements. Okay. Good. Okay, so here's A, here's B. So then now, what's the state of stress? What will be the state of stress at A, and what will be the state of stress at B location now? So I'm going to use precisely the coordinate system that we're using in it here. Okay, so for example, here's your Y. Remember, this is your Y here. Here's your Z, and here's X here. Okay, yeah. So here's the Y. Let's see if this is your Z at here, and so for example, actually, what's my Z direction? Well, Z is this direction here, right? Before we do this, let's still stick to the direction here. Let's still stick to this is X here, okay? And here's your Y, and here's your Z, okay? Yeah. So this is your location A at here. So think about this location A here. I will explode it, okay? Explode it here. So this is your A here. So this side, right, is the side, okay, on the cross section, and then you can think about the cube by finishing this cube at here. Okay, this is your A here. Okay, so at the A location, right, what type of stress exists at this A location? So here's your x-axis direction, right? Here's your x-axis. Here's your y, and here's your z. Yeah. Force. So yes, you have a force, you have a torque, you have movement. But now let's relate this loading to stress now, right? To stress. So at the A location, this is A location here, right? So you have a force, torque, and bending moment. What type of stress will be resulted because of the three loadings at here, at the A location? Yeah. Okay, but so force will make a shear stress, but that shear stress at A location will equal to what? So that this is basically back to the first lecture. When we have a beam and you have a loading condition, then you have a shear force at each location, right? And the shear force will cause a shear stress, and that shear stress is 0 at the top and the bottom, and maximum at where? At here, right? So you remember that, right? So this F, this capital F right here, will cause a shear stress, but it's 0 at the A location. Okay, yeah. It will be maximum at the B location, right? So there is no shear stress due to this F at the A location. Okay. So what about the what's the first? Let's say look at the bending moment. The bending moment will cause what type of stress at A location? Sorry. Tension. Yeah, sure. What name of the stress is called what? Normal stress, right? So let's draw a normal stress here. I call it sigma x. So sigma x will be a normal stress caused by the bending moment, and I draw it outside because it's tension. Okay? Yeah. So now you're done with F and M. Look at the torque. What type of stress will caused by the torque at the top edge? Shear stress. And what direction will be that shear stress? Look at the direction of the torque, right? It's if I draw an arrow, a vector here, it should be pointing to which direction? So here at this A location, torque is rotating like this. Positive Y? Like you mean like this? Yeah, that's right, Z, right? Yeah. So you should draw a direction here. So let's call this is tau xz because in the xz plane. Okay. And that's it. That's the results of the stresses because the loadings, right? And there are only 3. 1, 2, 3, right? That's it. And then you should try to balance out this thing at here. Basically, what balance this whole thing out essentially, right? To balance this whole thing out on this side, so you will have a sigma x pointing this way, and so for shear stress due to the torque, so you have a direction in this direction at here, right? So these two will balance out. Okay, yeah. And on that side of the wall side, you should have a direction on that side. That makes sense. And then on this side here, on the side back side here, okay, back end, you have a direction pointing that. Okay, yeah. So that's the stress element, and that is the state of stress at A location. Okay, yeah. Is that clear? Yeah. So at this stage, and then I always say at this stage, I'm doing things very accurately, step by step. Basically draw everything accurately. Okay, yeah. Later, okay, so often in time we just care about the absolute value. So you don't really care about the directions, things. So sometimes it doesn't matter. Okay, it's the absolute value matters. But at this stage, we'll do it right. So that's your A location here, right? So now let's think about the B location. So I'm going to draw a similar cube at here. Okay, here's a B location, and again, this is your X here, and here's a Z here, and here's a Y direction. Okay. Yeah. Okay. So for the B location, let's do one by one. Does the bending moment cause any bending normal stress at the B location? No, right? Because it's 0 at the B location, so that's out. And then the force, the shear force F, as we just said, it causes maximum shear stress due to this F at the B location. So you do have a shear stress which is pointing down the same direction, the F, right? And this one here, that will be, let's say, call it tau xy, for example. Let's call it tau xy1. Okay, yeah, because we'll have two actually shear stress. So this is caused by the F at here. Okay. And then you have a torque T. So the T goes around the center. At the B location, then you should have a similar shear stress caused by this torque, right? And the direction caused by the torque, T, at the B location, which direction? That's right, same direction, right? Good. So let's call this is another tau xy2, right? So let's call this is caused by the T. Okay. Good. So once you finish one side, and then you can finish the rest of the side. So the rest of the side basically is to balance this cube right here. Okay. Yeah. These are the state of stress at this B and A location. Is that good? Yeah. Okay. So now let's look at step number 3 now. Okay. So we'll look at each one of the state of stress. Okay. Accordingly at here. All right. Yeah. Now, if you look at the two state of stress at here, yes.
Why are we drawing the 3D stress?
Very good point. So I'm drawing a cube at here, but you're absolutely right. Your observation at here, this is essentially it's a planar state of stress, isn't it? Right? Yeah. So remember in the previous lecture we mentioned, what we do look at normally is a planar state of stress because the loading give us a planar state of stress. However, we are actually going to put this in what? In 3D, because we actually also consider the 3 principal normal stress, which is in 3D, right? Because that results in a completely different value for what? For the maximum shear stress. Remember that, right? So you have a planar state of stress, but you will put it in a 3D perspective, okay? In order to calculate the shear stress, maximum shear stress, okay? Yeah. But your observation is all right because you look at this one, these two here. If I look from the top, right? If I look from the top here, this is a planar state of stress, right? If this one here, if I look at it from the front, this is a planar state of stress, basically. Okay? Yeah, because there's no stress on this side, on only one perspective. Okay? So we might as well, when we draw the stress element, okay, when we illustrate, now we can probably just bring it back to this 2D perspective. Just to bring it, we'll have to look at calculate. When we calculate, we'll have to look at the 3Ds, right? Yeah. So we'll look at, we'll draw it in a 2D sense here, and I'll draw it very accurate. So for this case here, if I look from the top, here's X, here's a Z, right? If I look from the front, here's X, here's a Y. Is that good? Yeah. So now I'll label the stresses accordingly at here. Okay. So when I look at the front, you have a sigma x at here, the sigma x going this x direction, and then you have this tau here, tau xz going this direction, and here of course on this side here sigma x here. And for the B location, there are only two shear stress here, so you only have the shear stress is like that, isn't it? Right? Actually. Looking from the front, sorry, wrong direction. Okay. And this, let's call it tau, and in this case is equal to tau xy1 plus tau xy2. There are two shear stresses pointing to the same direction. So that's the state of stress and the presence of each type of stresses. Okay. Yeah. Now let's calculate each one of this. Okay, and put it into the actual values with the loading condition. Okay. So here's your sigma x, and sigma x is due to the bending moment, and that's the m, and it's at the top edge, which is basically times the radius of the rod and divided by its polar moment of the area, and this is your sigma x. And m we have calculated. The r here essentially is half of the diameter, and the g here is pi d to the power 4, and then divided by 64. Okay, so d is 1.5, right? And pi you calculate is a 6,000 pound force inch. So you got the two numbers already. Plug it in, and you got this much psi. You got this much of stress, normal stress. Okay. And then your tau xz there is your tau xz is tr over j. Okay. So sorry, this is not g. This is what the I, right? Yeah. So tr over j. So this is equal to t times d over 2 over pi d to the power 4 over 32. Okay. So this together you got 12,072 psi. And then for this stress element in here, tau xy1 is due to the shear force F. Now this cross section is a circular cross section. When you have a circular cross section, the maximum shear force, the maximum shear stress due to the shear force is 4V over 3A. Okay? V here is actually should be F, right? So it's the shear force here. Okay? So it's 4 times F divided by 3A, which is 755 psi. And your tau xy2 at here, okay, is caused by the torque, which is basically the same value now as the location A, psi. Okay. So that's all of the values individual stress. Okay. So you add these two up, you get your total tau xy equal to tau xy1 plus tau xy2, and which is 12,827 psi. Okay. Good. Okay, so now we have all the stress, and we're ready to basically to analyze now. Now you have basically two theories to use. One is MSS, and the other is the DE. For the first location A at here, in order to use MSS or DE, so I think we need one more step here. Let's calculate the two principal normal stress based on the sigma x and the tau xyz here. Okay, yeah. The formula for sigma A and B the formula you already use the subscript use the tau xy, but then that's in the perspective xy plane, right? So in our case, it's really just tau xz squared. Okay, yeah. So plug it in, and you'll get two numbers representing the sigma A and sigma B. What's sigma B? Okay. So for the first one here, apparently you see your sigma A is greater than 0, greater than sigma B. Right? So sigma A greater than 0, greater than sigma B. And given that condition, this is basically your sigma 1, this is your sigma 2, and here is your sigma 3, right? Yeah, the 3 principal normal stress. So this is where I'm putting it back into the 3D perspective, right? Yeah. So you're using the maximum shear stress theory. The safety factor is equal to SYT over sigma 1 minus sigma 3, and that gives us approximately 1.6. If we use the DE theory, we can calculate the Walmer stress first. That you can calculate also using sigma A, B. Okay. So that's your Walmer stress. And then the safety factor is SYT over sigma prime equal to 1.7 approximately. So this number calculation makes sense because this is slightly bigger than that, and that conforms with which one is the MS is a little more conservative, right? Yeah. Okay. This is the A location. So at the A location, you got the safety factor here. Both are greater than 1. So under this loading condition, the A location and here is safe. Okay, according to both theories. At the B location, so let's come back to the B location and here. I calculated the shear stress now. So the B location, there's only one shear stress. So if there's only one shear stress, and if you put it into the perspective, most circles, right? So here's your tau xy basically, and then here's your sigma b, and here's your sigma a. This is the type of most circles when you have a pure shear, right? And in other words, your sigma a is basically your tau xy, and sigma b is negative sigma a in this case. Okay. Yeah. Now apply similarly for MSS theory. So in MS theory here, you're basically calculating SYT over the maximum shear stress, so which is this value here. So that gives you this is 1/2 here. So 1/2 SYT over the tau max. Okay. So you probably wonder where's the 1/2? It's actually, if you remember, this is 1/2 over here and then 1/2 over here. Okay. Yeah. So this is where the 1/2 is from. Tau max is always sigma 1 minus sigma 3 over 2. Okay. And then DE theory, okay, you can literally do the same thing and calculate the sigma prime first. Okay. Now sigma prime, you can also try this formula, basically, which is based on the state of stress values. Okay. So that I don't remember what it is. No. Anyway, so you can calculate, so N equal to SYT over sigma prime, which end up as a 2.1. Okay. Yeah. So that's overall the safety factor, the A, and the safety factor at the B location. Okay. Yeah. Okay. So any questions so far? So at this stage, when you do your assignments, I would encourage you to do it very accurately by drawing free body diagram. You know, the direction of shear, the direction of the stress due to the loading. Okay, and do the calculation. Okay, so it's a good habit to have. Now back to the results here. If you look at the results here, the B and A, which one do you think is more critical? Comparing A and B location. A is more, right? Because the safety factor is smaller. Okay? Yeah. Now this actually is an important observation, and which is also I want you to bear in mind in the future. So the difference, if you think about it, right? The difference for A and B here is what type of maximum exists at A. So at A, the maximum is the bending moment, right? At the B, the maximum is the shear stress due to the F. So That basically what tells us here is, okay, yeah, this normal stress, okay, caused by the bending moment, okay. So we're basically comparing the two maximum conditions. So this normal stress caused by the bending tends to be more critical, okay, than the shear stress caused by the shear force. Okay, so essentially in the future, okay, especially later when we do the shaft design, okay, you don't need to look at both the top location and also the horizontal location anymore. You only need to look at basically that A location, the top location. Or in other words, you only need to consider the effect caused by the bending moment, okay? Because the shear force at the A location is 0, right? So that tends to be more critical, cause more critical conditions than the shear stress caused by the shear force. Okay, yeah. So anytime in the future, if we have a shaft, and we'll just usually pick this top location here, okay, and that tends to be more critical than B location. That's basically the conclusion from this example here. Okay, yeah. So that's all about the ductile material. Okay, yeah. Any questions so far? Now let's continue. And now look at the static failure for brittle material. Brittle materials. For brittle materials, and I think I mentioned about the nature of brittle material in this class. It's essentially, we consider it's an uneven material. So uneven material meaning the SUC is not the same as SUT. So the tensile ultimate stress is not the same as the compressive ultimate strength. Okay, yeah. And SUC usually greater than SUT. Okay? And for brittle material, it's about fracture. Okay, so the ductile material, the failure is about yielding, and the brittle material, the failure is about fracture. So we're going to present 3 different theories for brittle material. One is called maximum normal stress theory. So we call the MNS theory. And the second one, we call that brittle Coulomb mole or BCM theory. Okay. And the last one, we'll look at this modified mole theory. Okay, or MM theory. Okay. So we'll look at 3 of them. Okay. We'll look at also the connections among the 3 theories that are here. Okay. So let's look at the first one, maximum normal stress theory, MNS theory here. Okay. As usual, I'm going to write down the definition first, and then we'll analyze the definition. Okay. And also we'll sketch these failure boundaries, okay, or the safety boundaries, okay, based on for each one of the theories. So let's write down the definition first for the MNS theory. Failure occurs whenever one of the principal normal stress. Okay. So one of the principal normal stresses equals or exceeds the strengths. Okay. That's a very short statement. This is a statement for MNS theory. Okay. And then let's look at this sentence here and break it down to basically comparisons. All right. Okay. So what are we comparing here in order to prevent failure? First one of the principal normal stresses, right? So when this guy here equals or exceeds the strengths, and then this is the second quantity. Okay, yeah. All right, so one of this exceeds this. What does one of the principal normal stresses? So how many principal normal stresses? How many do we have? Yeah. 3, right? Yeah. Remember in the 3D case, you have 3. What are the 3? Sigma 1, sigma 2, sigma 3. Okay? When one of them, but the nature is, it's always you arranged like this, isn't it? Right? It's always arranged from high to low. Okay? Yeah. Strengths. Now you're talking about the strengths of the brittle material, and as we just said, there are only 2 strengths, SUT and SUC. Okay? Yeah. So basically, you're comparing this guy and this guy here to determine the failure conditions. Okay? Yeah. So if you look at this, one of the principal stress, I mean sigma 2 is out of picture, right? Because it's in the middle. Okay? When you have a sigma 1, sigma 2, sigma 3, here's a maximum, here's a minimum. So sigma 3 could be a negative number. Okay? Yeah. So basically, what you're comparing now is, here's the maximum, sigma 1. So that's the maximum here among the 3. You're essentially looking at is this guy greater than the SUT? Right? That's only a possibility because, you know, right, the other ones not possible, right? Or what sigma 3 is less than that. Okay? Yeah. So when you compress, it's a negative number, and if you compress too much, then it's a failure. Okay. So that's basically what this definition is telling us. If this happens, then you have a failure here. Okay? You have a failure. So let's summarize. This is a simple statement, but as what we have done here, we always basically put into the 3 different cases, right? We look at plain state of stress, which means you have a sigma A, sigma B, and a 0. But we look at each one of the case, okay, to be more specific. So the first scenario is when you have sigma A greater than sigma B greater than 0. Okay. So these 2 greater than 0. So sigma 1, sigma 2, and a sigma 3, right? Sigma 3. Okay. So when you have this kind of case, so if you think about it, so this is your sigma 1, sigma 2, and a sigma 3. And this is the principle for the this is the principle for MNS theory. Okay? So basically, you are not going to be able to have this case at all, right? Under this case number 1, because if I show you the Mohs circle, so if I show you the Mohs circle here, this is the case 1, so that circle must be where? So that circle must be on the right side of the plane, right? Must be on the right side of the plane. Okay, and then maybe I'll draw the circle a little bit closer to here. Okay. Yeah. And then your SUT, let's say this is your SUT here. So this is your SUT value. Okay, so this is your sigma here, and this is tau. Okay, yeah, mole circle. Yeah. So in order to determine the safety factor, so what do we compare now? You're only comparing between the SUT and the sigma A here, right? So that's basically, for this case, you're just comparing these two. The sigma 1 is sigma A. If this sigma A here, this is your sigma A. If sigma A goes beyond the SUT, according to MAS, then you got a failure, basically. Okay? Yeah. And now let's look at the case number 2, which is sigma A greater than 0 greater than sigma B. So for this case, your sigma 1 is here, sigma 2 is here, and sigma 3 is here. Okay? So if I draw a mole circle, okay, if I draw a mole circle, then chances are the mole circle, because this is greater than 0, this is less than 0, so the mole circle will be somewhere like this now, right? So basically it'll cross both planes, both the left and the right side plane. Okay. So here's your sigma B, and here's your sigma A. Okay. Good. So, and where's my SUT? It's here. So let's say we have our SUC over here. Okay, so this is negative SUC here. Okay. So if you think about this circle here, what could happen now? If you keep explode this circle, so there could be two possibilities, right? One possibility is this edge goes beyond here, and the other possibility is this edge goes beyond here. That makes sense? Right? So basically you need to look at both scenarios. You need to compare this SUT and sigma A. You also need to compare this SUC and sigma B. So you compare both of these. But you don't really take all of them, right? You only need the minimum value, okay, out of these two. The minimum value of that will be the safety factor. Okay. This is the second scenario. Okay. And the case number 3 is when you have 0 greater than sigma A and then greater than sigma B. So for this scenario here, so both sigma A and sigma B are less than 0. So your mole circle will definitely be on the left side of the plane now. Okay. So this mole circle will be always on the left side of the plane. And if that's the case, then the only possibility that you could have a failure case is when the sigma B goes beyond this negative UC, right? Yeah. And your safety factor is basically a ratio between these two. Okay. Good? Yeah. And that's it. That's the 3 cases. And we can summarize the 3 cases using that diagram as we always do. So you plot on the sigma A and the sigma B plane. Okay. And here is your 45-degree line. Okay. And first label your SUT at here, and then label your SUC at here, and negative SUC. Okay. Yeah. So for case number 1, right? If you look at the case number 1, so both sigma A, sigma B greater than 0, so which is here. So you're only basically looking at this vertical line here. And for second case, sigma A greater than 0, greater than B, so you're basically looking at is this portion here. Okay, both sigma A, second case sigma A is greater than 0, sigma B is less than 0, and the last case is this portion here. So together, you got this boundary. Okay, you got this boundary right here, and then you can make up the rest of the boundary here, which give us essentially a rectangular type of HS square. Okay, boundaries. Anywhere within the boundary, it's safe, and outside the boundary, it's not safe. Okay, yeah. That's MNS theory. It's very simple, right? It's very simple. Okay. Any questions so far? Okay. Okay. Before we move on to the BCM, the second theory, right? Let's observe a problem with this MNS theory. Okay, a problem. Yes. You mean it's too conservative or not conservative? Not conservative, yeah. Right. It's not conservative in certain quadrants, okay? Particularly in this quadrant here. But why? Right? What is it this MNS theory is not considering it here? Okay? Why? So I think you should focus on the circles, the mole circles here. Okay? So if you look at the mole circles here, particularly look at the second case, this case. Okay? This case here. Can you draw mole circles within this case number 2? This is how I draw it here, right? What else can you draw? You could draw like this, isn't it, right? Or you could draw, okay? But as long as the two edges are within here and there, then you're safe according to MNS. Does that make sense? Okay? But what's the problem now? If I draw a mole circle here and here, that circle become bigger, right? When you have a very big circle, it also has a very big what? Shear stress, right? So that's what the MNS theory is not considering here. It didn't consider this shear stress for the second case. And it could very well that the shear stress already exceeds the shear strength for the brittle material. Okay, yeah. So that's why we need to modify this MNS theory here. Okay, brittle material typically, as said, fail due to normal stress, right? But if you don't consider the shear stress, because the shear stress is so big, it actually exceeds the shear strength. You still have a failure due to shear stress. Okay, yeah. So that's what the second one, the BCM theory, is trying to do. It's trying to modify this MNS theory. Okay, yeah. So the BCM theory are initially based on the so-called Mohs theory, which is proposed in 1900. Okay, so it's a guy called Moh something. So what Mohs theory states is, it's a very simple theory, right? It's a very simple theory. So what Mohs theory states is, okay, so you want to predict a failure of a part of material, right? So let's do experiment, right? Let's do experiment. And you could do experiment, you could do a basically tensile test. Okay? So you could do a tensile test, right? And tensile tests give us, so you could do a tensile test at here. Okay, that's Mohs circle for tensile test. Its tangent is always 0 here, right? Yeah. And tensile test give us the yield tensile strength. And you could do basically a compressive test. So the compressive test, okay, that's the Mohs circle for compressive test. A compressive test will give us basically the compressive strength. Okay. And then what else could we do? We could also do what? We could also do a torsional test, right? A pure shear basically test. and you do a pure shear, then you got a circle centered around the origin. So those are the three most common type of tests you could do on the parts and material to obtain a certain quantity specifically, right, corresponding to that type of test. Okay, yeah, or certain strengths basically. So the second one here, you could do a torsion test. So 3 different tests, okay, and after you've done the 3 different tests, and then we could basically look at the 3 most circles and try to draw some kind of boundaries, right? Some sort of boundaries, or we call that the failure envelope. So, okay. And you could do a curve fading or whatever. So basically come up with some sort of a failure envelope here. Essentially what it means is whenever you have a Mohs circle within this envelope, then it's safe. If you have a Mohs circle representing certain loading conditions that's outside this envelope, then it's unsafe. Okay? Yeah. So that's the idea here, to try to create a failure envelope based on the 3 different tests, and within this envelope is safe, and outside the envelope is unsafe. Okay, yeah, that's Mohs theory. And then of course the challenge here is, what would this failure envelope look like, right? I mean, you could draw the curve fitting could come up with maybe a quadratic or cubic. What type of curve? Any kind of curve could be used to fit this envelope there, right? So that's a challenge. So, how do we determine this envelope here, right? So the brittle Mohs circle essentially here is BCM, and here is. Let's take a shortcut. So let's take an easy solution at it here. Okay, easy solution. So the easiest solution for BCM basically saying is, okay, so here is your tensile test, and here is your compressive test. Okay, yeah, and without worry about the torsional test. Okay, without worry about the torsional test, we create an envelope by drawing 2 tangent lines. Okay, 2 tangent lines across these circles here. Okay, so BCM takes a really easy outlet here. Just draw 2 tangent lines, okay, for the envelope. So the failure envelope right here. Okay, it's a line. Okay, it's not anything like a curve. And of course, you have here's your negative SUC, and here is SUT here as the 2 boundaries on the left and the right. Right? Okay. Yeah. So basically, now if you think about it, here are the 2 tangent lines, which are the envelope. Then if you have any Mohs circle, that in the case number 2, and when it starts to expand, and if it started to become a tangent to this envelope, and that's the failure condition, right? Yeah. If you have a Mohs circle, the green one goes beyond this envelope, then it's the failure. Okay. Yeah. And this is basically BCM theory. So I'll just write down the definition in here. So failure occurs when Mohs circle describing the state of stress becomes tangent to the failure envelope. Okay, yeah, that's all about it. So if it's become tangent to this red line here, that's envelope, and this is also here, right? Then you have a failure. Okay, that's BCM. Okay, so now let's look in the details here. Let's still look at each cases, right? That's originally case number 1. Okay, so for case number 1, there's no change. So all you do is you still compare between SUT and the sigma A. Okay, there's no change. And for case number 2, so there's a little bit change now for this case now. So case number 2. So case number 2, basically coming back to this diagram here. Okay, that's the green color corresponding to case number 2. And the failure, basically, when it becomes tangent to the red line at here, it'll become a failure, right? Yeah. So in this case here, what we do is we do a little bit derivation at here, which I'll skip the detail. So for example, okay, if this is a tangent point B, if this tangent point D, and the green becomes tangent at here, let's say call it tangent point C, okay, and you do have a center for each one of the circle at here. So there's 3 centers for each one of the circle. So let's say this is O3, O2, for example, O1. Okay, yeah. And the green one here, so this side here is your sigma B, and this side here is a sigma A, right? So this green one, the sigma AB represents the state of stress, right? So here's sigma A, here's sigma B. Okay, yeah. So if you plug in this one here, and then you look at my lecture notes, I have a detailed derivation here. Basically, we can use some simple high school geometry at here to derive these failure conditions at here. Okay, yeah. So you will be able to derive a failure condition. In this case, is so the boundary is sigma A over this minus sigma B over SUC equal to 1. Okay, so this one here is the boundary condition. When it's equal, when this whole expression is equal to 1, that's basically at the failure boundary condition. Okay, yeah. And of course, you want to not just 1 here, right? You want to calculate the safety factor. So the safety factor will be will be just 1 divided by this quantity at here. Okay, this quantity. Yeah. Good? Yeah. Okay, so that's case number 2. And then case number 3, we have a 0 greater than sigma A greater than sigma B. And no change for this case. It's still the same as MNS theory. Okay, still the same. Negative SUC over sigma B. Okay? So if I try to illustrate these whole 3 cases on a sigma A and a sigma B plane. Okay. Here is your sigma A equal to sigma B. So the first side, the first quadrant, there's no change. This is your SUT. Okay. And then the third quadrant, there's also no change. This is negative SUC. Okay. It's this quadrant here, the fourth quadrant here. This quadrant, basically, it's this line here. This is the boundary. This is the boundary. And that boundary corresponding to this line here. Okay. So this boundary here, so this line here corresponding to that red line here. Okay. And then you can finish the rest of the drawing, okay, by mirroring it. So overall, you got a hexagon type of plot right here. Okay. Yeah. Good. So that's the second theory, BCM theory here. Okay, BCM. So let me finish the theories. I think there's only one here, so I think it's we could finish this, and then we'll look at examples at the beginning of next lectures. Okay, so the last one here is called modified modes theory. Modified mode theory. Okay, so MN theory. Okay. MM theory. And what is the modified mode theory here? Okay, yeah. Okay, so the modified mode theory is based on an observation from experiments. When people do experiments, and then they notice that, okay, in the fourth quadrant, in this quadrant here, okay, in this quadrant. So experiments show that in tensile stress dominant, okay, tensile stress dominant situations, okay, failure is due to tensile stress only. Okay, failure is due to the tensile stress only. So let's think about what does it mean at here. Okay, so if you think about this one here, right? First of all, what does tensile stress dominant only, right? What's tensile stress dominant? If you look at the fourth quadrant at here, so basically, when you have a tensile stress dominant, that basically means your sigma A is greater than 0 and greater than sigma B, right? This is dominant. This is bigger than that. Okay, this is bigger than that, and also the absolute value of this sigma A, okay, is also greater than absolute value of the sigma B. Okay, yeah. So that's basically what tensile stress dominant means. So within this quadrant, it could be this is positive, this is negative, but it's possible that this absolute value of this is greater than absolute value of the sigma B at here. Okay, yeah. So that's basically what tensile stress dominant here. And if this is the case, basically, right? If this, then the failure is due to the tensile stress only. Okay, that's basically what this means at here, okay, and what the experiment shows us. Okay, yeah. So let's think about basically think about from the structure point of view here now, right? Yeah. So here's your sigma A, here is sigma B. Here is sigma A equal to sigma B here, and this is your SUT. Okay, first quadrant, there's no change in the first quadrant. Okay, no change here. Okay, and now I'm going to draw another one in here. Okay, I'm drawing another one here. So this line here, I call it sigma A equal to negative sigma B. Okay. So the reason I'm drawing this line here, so I can have a clear distinction between what do we mean by the tensile stress dominant in this quadrant, right? In this quadrant. So if you look at this line, this is the line when sigma absolute value sigma A and sigma B are the same, right? Now, if you look at this portion above this line here, the portion over here, whenever you pick a point here, 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 right? It's very naturally what? Sigma A is greater than sigma B, right? Any point over here. Okay? So this portion is the tensile stress dominant portion. Okay? Yeah. And the observation is the failure is due to tensile stress, so due to this. So basically the modified mode theory says is keep going, right? draw a vertical line here for this portion. Okay? Yeah, that's basically what the modified mode is doing. And here's your SUC at here. Okay? Yeah. So what happens if absolute value sigma A becomes less than absolute value sigma B? Basically, it's not a tensile stress dominant anymore. Then what do? The most modified mode theory is connect from here to here as a straight line. Okay. So then the rest of the things here is the same. Okay. So that's overall what the M theory looks like. Okay, will be like this now, right? So this is slightly different in this quadrant at here compared to the BCN. Okay, compared to BCN. Now, in terms of the interpretation here, right? In terms of the interpretation, I forgot to bring the handout. I actually printed out. I forgot to bring it here. So I have a summary, basically. Corresponding to each one of the theory here. So this is the MM theory here. So you have all different cases and with different boundary lines here. For each case, you have basically line equations describing the boundaries here. Okay. So this is your guidelines in terms of following this formula here to calculate safety factors. Okay. I'll bring this next week. Okay, bring next week for the handout. And I'll go through an example for the brittle material, which is very similar to ductile materials. Okay, just follow the formulas with you. Any questions? Okay, good. Yeah, come on.
Is everything to the left of